Okay, so I didn't change my title. Right, so this video is the acidity of a carboxylic acid. So really, this chapter deals a lot with the inner conversion of carboxylic acids and their derivatives. But it's important to point out, right, as you would expect from the name of the functional group is a carboxylic acid. So acidity is going to be if you look at the chemistry of any carboxylic acid, it's probably dominated by the acidity of that proton. Okay, so on the top here, I've just put an acid-base equilibrium between acetic acid and water. So if I dissolve acetic acid in water, what happens? Well, water is a weak base, can take this proton, and I get acetate and hydronium. So this is acetic acid. Okay, the pKa of acetic acid is 4.75. Well, the pKa of H3O plus is somewhere in the vicinity of 0. Okay, so the left side of this equation is favored. And by a fair amount. You can get the equilibrium, you can work through all the pKa. So you can work out the equilibrium constant by taking 10, right? P is a log function. So we're going to take 10 raised to the power of one of the pKa's, the product pKa, minus the starting material pKa. So in this case, this would be 10 to the minus 4.75, right? And that would indicate if the equilibrium constant is less than 1, the left side is favored. And so these pKa's, if you do an acid-base reaction, if you're doing an acid-base reaction and you know the pKa's, you can actually measure the equilibrium constant, or you can estimate with pretty high degree of certainty the equilibrium constant just by comparing the pKa's on either side. But the pK, and like I said, you guys should know that carboxylic acids, most carboxylic acids where you just have sort of an alkyl group here or an aromatic group here are going to be somewhere between 4 and 5. They're in that ballpark. They can go quite a bit lower if you put strongly electron withdrawing groups on here. So, right, the carbon-chlorine bond is polarized. We're trying to, you stabilize the O minus or you make this OH more polar by withdrawing electron density. That's how the carbonyl in the first place makes that OH so much more acidic. Remember, ethanol has a pKa of 16. Okay, so if you put a carbonyl on here, that makes the proton like 11 orders of magnitude more acidic. 11 orders of magnitude is a lot. If we add a chlorine to acetic acid, so this is chloroacetic acid, the pKa falls to 2.9. Yeah, I just wanted to double check a number. I didn't write it down. If we put 2 more chlorines on here, the pKa for trichloroacetic acid falls all the way to 0.9. Trichloroacetic acid is now like a strong acid. And in fact, trichloroacetic acid is used to precipitate proteins in biochemistry quite a bit. And then I just wanted to talk about a few mathematical, organic chemistry is not a real mathematical quantitative class. But you can take a class called physical organic chemistry if you want after this, where we get into a lot of mathematics involving organic chemistry. But this just comes out of the Henderson-Hasselbalch equation that you would have done in general chemistry. pKa is actually defined, the way we measure a pKa, it's defined as the pH at which the concentration of the conjugate base is equal to the concentration of the acid. So right, if we have this at pH, hang on. I said when we first did this, the pKa on the left is higher than the pKa on the right. So the left is favored at equilibrium. If I just add acetic acid to water, the equilibrium favors the starting material. But what if it's not water? What if the pH is buffered at pH 4.75? Which side's favored? Well, what we learn here is this is now not favoring either side, but we're going to have a 50-50 mix. So if I take a buffer of 4.75, pH 4.75, and I add a little bit of acetic acid, it equally deprotonates and protonates. So again, at pH, when the pH equals the pKa of the acid, that acid is 50% deprotonated, 50% protonated. And then from there, right, if I have a 50-50 mix and I add acid, I add protons, right? So the pH is going to go lower now. Lower pH is equals acid. If I have a 50-50 mix, acid and conjugate base, and I add protons, I'm going to protonate the conjugate base. So when the pH is below the pKa, when it's lower than the pKa, I have a higher concentration of acid than conjugate base. All right, on the other side, if I have a 50-50 mix and I add base, I'm going to pull protons off. So when the pH is higher than the pKa, that is when the conditions are more basic than the pKa, I'm going to have more deprotonated acid, that is conjugate base, than I have protonated acid. And again, that's this equation down here, which is really useful, that the equilibrium constant is going to be 10 raised to the power of 1 pKa minus the other pKa, and just adjust for which side you want favored. And structurally, what are we going to do? I'm probably going to ask you a few times to compare acidity. Like, which molecule do you think is more acidic and why? So again, the more you can stabilize an O-, or the more you can polarize this OH bond, the stronger the acid's going to be.